Okay, so this problem reads, part A, calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour in a distance of 120 meters. So this is a typical distance for a non-panicking stop. And then we're going to compare that to what would be the kinetic energy, or the force, excuse me, if the car came to an abrupt stop by hitting a concrete wall. And so that compressed the car by 2 meters, so it was brought to a stop in 2 meters. So we're going to calculate the force in both those scenarios and then compare them to see how much larger the force is if you come to an abrupt stop. Excuse me, we are going to use the work energy theorem in association with kinetic energy only. We're only going to look at how work causes changes in kinetic energy in that method of that work energy theorem. So the work energy theorem tells us that the net work is equal to our change in kinetic energy of the system. So that's all the forces acting. And so we want to know what that total force is acting on the car in this case, so we can look at the work done by that total force, whatever is the source of it. The change in kinetic energy, remember, is 1/2 mv final squared minus 1/2 mv initial squared. So our difference between our initial and our final kinetic energy. And if we want to look at kinetic energy, we have to make sure we're using standard units. And so we want to remember that our speeds need to be in, I think I might have said velocity. Our speeds need to be in meters per second. Well, our speeds are not in meters per second. So let's do that conversion first. We know that the initial speed of the car is given to us as 90 kilometers per hour. So let me convert that to our meters per second. We know in 1 kilometer there are 1,000 meters, and in 1 hour there are 3,600 seconds. And so this initial speed of the car in meters per second is 25 meters per second. What about the final speed? Well, we're told it comes to a stop. So we know that our final speed is 0 meters per second. All right. So let's look at these two situations. Situation number 1 is we are stopping that car in 120 meters, and we're interested in the force exerted by that. So we know what we can determine the work done to stop the car is equal to the change in the kinetic energy. So the work done is equal to 1/2 m times v final squared, the speed final, minus 1/2 m v initial squared. We know that the final speed is 0, so that term is going to go away. And we find that the work is equal to minus 1/2 the mass times the initial speed squared. So minus 1/2 our mass of 950 times our initial speed of 25 squared. The work then acting on that car is minus 2.997 times 10 to the 7 joules. What does that minus tell us? Well, it tells us that the force, net force acting on that car is working opposite the direction that that car's motion is being changed, opposite the direction of the displacement. Now we also want to, this is our work. The problem's asking about force. What's the net force acting on that car? Well, we know that the work is equal to the force times the displacement times the cosine of the angle. Well, we're going to say the net force is acting in the same direction as the displacement because the kinetic energy is changing in that direction. So the work has to be acting in that direction. So we can solve for the force, and because it's in the same direction, well, opposite direction, negative 180, we know that the angle is at 180 degrees. So we have minus 2.97 times 10 to the 7th is equal to the force, and it's over a distance of 120 meters. So minus 2.97 times 10 to the 7th divided by 120 is our force, and that gives us a total force of 2,470 newtons to the left. Opposite the motion is what that negative tells us. So the magnitude of the force, the strength of that force, is 2,470 newtons. All right. What if the car instead hit a concrete bumper? Well, let's first look at what's similar about those two situations. We know that the change in kinetic energy is the same. It's going from moving at 25 meters per second to 0. So because the change in kinetic energy is the same, the work is the same. So for part B, the work, the net work acting on that car is the same. Negative 2.97 times 10 to the 7 joules. Same amount of work, bringing it to a stop. But it's happening over a much shorter distance. And so that's where the interesting part comes through. We know that net work is equal to that net force times the distance times the cosine of the angle. And we've already talked about how this angle's at 180 degrees. So we have minus 2.97 times 10 to the 7th is equal to my net force times 2 meters. This is stopping in a distance of 2 meters. So minus 2.97 times 10 to the 7th divided by 2 is equal to my net force, which if I calculate that is equal to 1.48 times 10 to the 5th newtons. Really big force, 1.48 times 10 to the 5th newtons. All right, well, what's the ratio of those two? We know that if we're interested in looking for part C, force 2 relative to force 1, we find 1.48 times 10 to the 5th divided by 2470. We find that that is 60 times larger if you run into that concrete barrier. Now, I did just notice this is negative. Again, that means that force is to the left, opposite that motion we were talking about. So I apologize for dropping that negative. The magnitude of the force, like we did in part A, is that 1.48. So if we look at the ratios of those magnitudes, I'll just put my magnitude lines on there so I'm legit, that we see it's 60 times more force. Lots of force. All right, so we did this problem through work and energy. It turns out you can also do this problem using our kinematics process. You might recall with kinematics, we talked about changes in motion. It's a change in motion. We could connect that kinematics to the forces, do our motion analysis, do our force analysis, and we'll still be able to determine these two forces. But if we think about the power of work and energy, and as we move forward, even conservation of energy, the process is really straightforward. And so we want to be practicing that use of energy. All right, recognizing we're dealing with changes in kinetic energy. That's being caused by work. That work is being done by a force. And we can sort of do this problem in one fell swoop instead of all those pieces with kinematics and forces. All right, good job.